Hello, I'm Stephen Oliver from Navitas, here at Bodo's wide bandgap event to talk about GaNFast, architecture and performance in high-power systems. The move from the old legacy silicon FET to gallium nitride is not easy if we have a discrete approach. With a discrete GaN device, we have the exposed weak gate, which must be protected, controlled, which leads to higher cost, complexity, slower speeds, and lower efficiency. Only with the monolithic integration of GaN driver and GaN FET do we have zero gate source loop impedance, which means this fantastic high-speed material can run at high speed with high efficiency and high reliability. At Navitas, we have shipped over 30 million GaNFast Power ICs, with zero reported field failures. So this is the GaNFast revolution. And what's next? So after the GaNFast revolution, we have the GaNSense evolution. Now, as well as the monolithic integrated drive and FET, we have sense technology. We have the highest efficiency with lossless current sensing, autonomous standby. We have the highest reliability through system monitoring and real-time protection. Taking a more detailed look at lossless current sensing, in a traditional system we have a resistor. Resistors are sources of loss, and when we need a plain resistor in a current path simply to measure the current, we end up doubling the resistance of that path, which means doubling the loss. By moving the current sensing onto the GaN device itself, we halve the resistance in that leg, and so we halve the loss and remove a hotspot of that current sense resistor. Here you can see by going from a standard GaNFast device to the new ones with GaNSense technology, we can increase efficiency by 0.5% and eliminate the RCS hotspot. One example of protection with GaNSense is in overcurrent protection. Here we go from detection to protection in only 30 nanoseconds, which is 10 times faster than a discrete implementation where the system information must be passed back to a system controller, which then decides what to do with the powertrain. So here, GaNSense 10 times faster than a discrete approach, further improving the reliability of high power, high density systems. The GaNSense technology is already in mass production, with customers including Lenovo for the Yoga, and here Xiaomi for their new 120 watt Ultrafast charger for the Note 11 Pro Plus. This is a flagship phone with a 4,500 mAh battery using graphene lithium-ion technology and a 0 to 100% charge time in only 17 minutes. Here the GaNSense devices are used in the DCM Boost PFC and also in a high-frequency DC-DC step-down. Using the high frequency, we can use planar transformers to improve the power density and the efficiency and the reliability in manufacturing. Let's look at how GaNFast technology with GaNSense can be used in higher power applications. In data centers, going from silicon to GaN can be a 10% increase in efficiency for the whole powertrain from AC to processor. For a data center operator, this is big news. Every 1% in efficiency increase saves on electricity bills. And we estimate that by converting from silicon to gallium nitride, we can save the industry over $1.9 billion per year in electricity costs. As you can see in the center, when we go from a silicon-based power supply to a gallium nitride Power IC based power supply, we improve the power density by 2x, we have a 38% reduction in the loss, and we do this with high frequency, high power density, totem pole and LLC configuration. CompuWare of Taiwan is the world's #1 in high efficiency server power supply. They have evaluated Navitas GaN Power IC technology and believe it is the future for data center power. In some data center and industrial applications, we have a 400-volt DC bus and need to convert to lower voltages. Here we see the progression in the standard quarter brick form factor from silicon to hard switch GaN and then soft switched GaN Power IC applications, all the time increasing frequency, increasing efficiency, and increasing power density. Now up to 6 times more power in the same quarter brick form factor than the original silicon design. Returning to the AC input, here we see the standard 1.2 kilowatt design. In this case, this is a CCM totem pole PFC followed by LLC, achieving 1200 watts in the standard form factor, which is 2.3 watts per cc. Here we're using the NV6128 GaNFast Power IC, which is a 70 milliohm device in 6.8 millimeter QFN for the high frequency leg of the totem pole and the primary of the LLC. When we look at the efficiency, we can see that we meet the titanium class, the highest grade of server power supply with margin, and we do that in a standard form factor and a very simple construction. Here you can see the central daughter card containing those high voltage GaN Power ICs. So we have a very simple design, very high performance, and per a customer quote, this is a lower cost than doing it with silicon. So a great result for gallium nitride. Thank you for watching this presentation on GaNFast architecture and performance in high power systems. I would also like to thank Bodo and Holger for arranging this wide bandgap event, and I hope that we can all meet again face to face for the next one. Thank you.